This is the fourth session of Philosophy 201 Introductory Logic. In the first few sessions, I told you that our goal this semester is going to be to learn how to give arguments that are completely logically rigorous. That is, in our technical terminology, to give arguments that are valid, where a valid argument is one such that if your premises are true, your conclusion is guaranteed to be true. So it's an airtight connection between truth of the premises and truth of the conclusion. And our second goal being that we want you to be able to evaluate other people's arguments and judge whether those arguments are valid or not. So we'll attack this from a couple different directions. The main direction we'll attack this from is writing proofs. So what is a proof? A proof, if it's successful, is an argument that proves the conclusion. Again, keeping in mind that we've factored out the question of whether the premises from which one starts are true. So the claim is that the conclusion would be true if the premises were true, but we want to make sure that the steps we take in the argument are logically rigorous. So we're going to be writing proofs. Now, you've certainly written proofs before in your life. For example, if you took a geometry course in, say, junior high school, middle school, something like that, you'll have learned to give rigorous arguments, that is, proofs where the content was geometry, where it was about shapes. What we want to do, though, is we want to learn how to give rigorous arguments, that is, proofs, about any content whatsoever. So we want to give the completely abstract and general form of a valid argument. Now, in the next few weeks, we will focus in on arguments that are valid because of their propositional form. So in other words, the reason they are valid is because of the way those propositional connectives and, or, if, comma, if dot, 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 then dot, 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 those connectives function. And that will occupy us for a while over the next few weeks. And the second half of the semester, we'll come back and talk about something called quantifier form. But let's leave that aside for now, quantifier form. And we'll just talk about propositional form today. So what is our goal? Well, let's be ambitious for a second. Ideally, we would like to be able, for you to be able to reproduce every valid argument form. I wrote here, though, reproduce all and only valid argument forms. So there's two sides to this goal. The one side is safety. We don't want you thinking you're giving rigorous arguments, but not. A lot can go wrong if you do that. In fact, in one sense, your whole life can go wrong if you do that. If you think that you're making a rigorous argument and you go from things you know, but you draw a conclusion that you can't know because, for example, it's false, a lot can hang on that. So we want you to be safe, but we want you to get all of the valid arguments. That is, we don't want you to be so safe that you don't say anything, that you don't believe anything. We want you to use the full power of logic at your disposal. So it's an ambitious goal, but it's a goal that was going to be very controlled and safe. So how do we do that? Well, I'll come to that in just a second, but let me give you a couple examples. So if you look down there under the examples, first of all, we should be able to, if we do things right here, we should be able to prove things like P or not P. So that's one of the most simple tautologies. That is something that's true no matter what. That's something that should be true in any circumstance, and so therefore it's something that should be able to be proved by logic alone. So we want to make sure we can prove that. On the other hand, we don't want to be able to prove anything. In particular, for example, we don't want to be able to prove P and not P, because that can never be true. So you don't want to be able to prove it's true. If you've proven that it's true, you've done something wrong. Okay, so those are kind of examples, although those examples are a bit extreme because our typical example is an argument that is something that has premises and a conclusion, and we want to know when do we have a valid argument from those premises to that conclusion. Okay, how will we attack this problem? Down looking at the bottom of this slide, we will teach you to generate valid arguments. How will we do that? We'll approach it in almost a chemical fashion, so to speak, the method of analysis, where you start with atoms, that is the smallest units of valid argument. Those will be one-step basic valid arguments. I'll give a couple of those to you in this session. We'll grow that list over the next few sessions. Then out of those basic building blocks of one-step valid arguments, We'll then string those together to form these larger molecules, in other words, longer valid arguments, with the claim being every valid argument whatsoever can be constructed in this fashion. So that's going to be our overarching plan of attack. But now let me be even more specific, and this is going to require a little bit of what you might consider to be philosophy talk. So there's some deep thought behind this whole thing we're doing here, and one can spend a lot of time reflecting on how would one know what the laws of logic are. And that's an interesting question. It's not a question we will get into deep debates about right now, because it's more important that we learn what the laws of logic are, and then we can come back later if one wants. One can come back and think about how in the world did we know that? Just in the same way that a child learns how to speak before it starts learning about the theory of speech. So the overarching idea here, though, and the main reason I'm telling you this is mostly so that you will have a guiding thread. So you don't feel like it's chaos. You see, okay, we're marching through systematically. So for propositional logic, that is the logic that depends on how propositions are combined using connectives, the idea is the basic, those atomic valid inferences, every one of those either introduces a special logical word or it eliminates a special logical word. What do I mean by a special logical word? I mean one of those words that are used to put together propositions into larger complexes. So the word and, the word or, the phrase if then. So for each of those special logical words, we'll have an intro rule, introduction rule, and an elim rule, an elimination rule. So it turns out to be a very elegant way of framing this. Okay, so now last bit of preparation for what we'll do today is I'll tell you for the next few sessions, couple sessions, we'll do what I call deducing. That is where I just tell you how to draw inferences from given data. So deducing inferences from premises, from assumptions that are given to you, that will give us the rules of and elimination and introduction, or introduction, if elimination, which is also called modus ponens, double negation, introduction, and elimination. Those are all just simple deducing rules. Those are rules that let you take sentences already given and derive new sentences from those. Turns out with just deducing rules, we can't get every valid argument. So then we're going to have to do something a little bit more sophisticated that goes under the heading supposing, and that you'll see matches one of the chapters of our course textbook, How Logic Works. And I won't say more about that right now other than to tell you the rules we will develop there. The rules of inference, the logically valid arguments, involve introducing if-thens, so that's sometimes called conditional proof, and also reductio ad absurdum, and finally, or elimination, eliminating disjunctions. So those will all be under the heading of supposing. Now for your reference, a list, so all of these rules are discussed in the textbook. They're introduced sequentially. I won't introduce them in lectures in exactly the same sequence they're in the book. I imagine you are intelligent enough to take 2 rows of things, same things that are slightly differentially ordered, and put them back in order. But if you look on page 231 of the textbook, there's a summary of the inference rule. So you can always refer back to page 231. And in fact, it's something that you almost certainly don't need to memorize it, because the most important way of learning these rules will be by giving valid arguments, by writing down proofs. Okay, so in truth, actually, there's a rule that comes before all the other rules. And in fact, it's what you might consider to be sort of a rule just that you're permitted to start writing proofs in some sense. So typically, at the beginning of this class, what will happen is we will give you premises, we will give you a conclusion, and we will ask you to derive the conclusion from the premises. How should you begin? Well, we give you permission, not surprisingly, it would be odd if we didn't, to take the assumptions we give you and write them down. Now, for now, we'll call that, oddly enough, the rule of assumptions. In other words, if we ask you to write something down, you may write it down. And how do you do that officially? Well, if you look at this slide, suppose that we give you premises x1 to xn. and we say, please derive conclusion Y from those premises. How should you begin? Now, I actually want to take that back and say not should, because the truth is logic, as we'll see, is more about permission than restriction. So what you're permitted to do is write any of those assumptions on a line and then write to the right of that assumption an A that indicates that was given to me. That's an assumption. If you've done geometry arguments before, that would be a given. Okay, so here's a typical line of a proof. If you look here, if you look at line 1, just get some color that will show up here. So this is a line right here of a proof. Okay, so the line is numbered. Every line of your proof will have a number. Here's the sentence that occurs on the line, x1. So that's a sentence. Now, in truth, let me be clear, the premises we give you may be complicated. For example, I may give you a premise that looks like this. So suppose that here's line 1. There could be a premise that looks like this. If P, then Q and R. So if I hand that to you and say, you may assume that, then your first line might look like that. Assumption, if P, then Q and R. Okay, so in this case here, x1, x2, all the way up to xn could be very complicated sentences. I've just used x1 to xn to indicate there's some other sentences. You're allowed to write them down as assumptions. That's the rule of assumptions. Okay, as you see here at the bottom, this column here, so there's 3 columns in the proof. There's the column of the numbering. There's the column, each line in that column, each row has a sentence. That's what's asserted there. And then on the right-hand side is the justification. So all lines will have a justification. In this case, all of the lines are just assumptions. Okay. Now, for example, if I told you the utterly trivial problem, I said derive a sentence P from the assumption P, then your proof would just be 1 line long. You would take the permission I've given you to assume P and you would write it down and then you would have P. Okay. Okay. So we have the rule of assumptions that just gives you permission to write down the things you're taking for granted, the premises of the argument. Today, or in this session, we'll look at the 2 rules that are associated with the word and. There's an and elimination rule that is for getting rid of and there's an and introduction rule that is for putting and in. The and elimination rule is as simple as you can imagine. It just says if you have already a conjunction, then you may, on a subsequent line, any subsequent line, you may peel off either one of the conjuncts, that is the things that are put together by the conjunction, write it on a subsequent line, justify it by and elimination, always pointing back to the line from which you got it. So I'll write it in a very abstract form here before we go on and use it. Okay, so in an abstract form, it would go like this. On line, I'm going to write now my line number in parentheses just so I keep clear. So here's line N. Who knows what that is? It might be line 1, it might be line 17, it might be line 32. There's some or other conjunction that occurs on that line. Now, at this moment, I have to explain something because suddenly Greek letters have appeared and you might think I'm just showing off that I learned the Greek alphabet at some point. But no, actually, there's a method to the madness here. And the method is this thing, phi and psi, could be, here's an example of that. It could be, for example, P and Q. Now, what's the difference? So P is, in fact, over here on the right-hand side, P is actually a element of a new language. So it's an atomic sentence of a new language. The Roman consonants, P, Q, R, S, those are definitely atomic sentences of this new language. Okay. However, phi and psi in this picture could also be something like this. Let me write on the right-hand side just an arbitrary thing I chose, P or Q and Q arrow R. That's also an example of phi and psi, because the idea here is phi is a variable that points to any sentence whatsoever in the new language. The new language whose sentences are made up of these constants, these capital letters, and putting those together. So this on the right is an example of phi and psi, because in fact, here's a phi, that's a sentence. Here's a psi, that's a sentence. They're put together with conjunction. So this thing on the right has the proper form on the left. Okay, that's a bit complicated. If you see it enough times, this will just start to come naturally. Don't think too hard about the philosophy behind this right now. Just think, what am I permitted to do? What you're permitted to do is if a conjunction occurs on line n, on any subsequent line, I'm just going to write n prime, because who knows what it is. So suppose that we have line n prime down here. What I'm permitted to do by this rule is I'm permitted to write phi. Then on the right, in the column of justifications, I would write n and elimination, which my shorthand here is just the wedge, the and symbol, and an E for elimination. So that's the standard format for and elimination. Now, I could also have done it the other way around. So this rule is symmetric. You can peel off the right conjunct, the psi in this case, instead of the phi if you want. Okay, so that's very simple. Now, we'll look at a couple examples in just a minute, but actually so our examples won't just be utterly trivial, let's go ahead and look at and introduction as well. Okay, so and introduction, as you might expect, it's the sort of reverse of and elimination. But of course, you need, in order to get a conjunction, you need both conjuncts. So this rule and introduction requires that you get two lines, and then on any subsequent line, you can write a new line with the conjunction of the things on those two lines. So the typical case will look like this. It will look like there's a line n with some sentence, who knows, phi, some or other sentence. A line n prime, could be far away, could be right after n, could also be before n, doesn't matter which order they come in, but there's some other sentence psi. Then I'm going to write n prime prime. Sorry for the primes. The point is just I don't know what these lines are. There's some or other lines, but n prime prime comes after n and n prime. Then you're permitted to write phi and psi, and the justification is n prime, and then wedge I, that is conjunction and introduction. Okay, so that's it. There's our and elimination rule and our and introduction rule. Okay, so let's put these to work, and we'll do a couple proofs. Okay, so let me explain the notation here, because this will be the notation we'll use for the rest of the course. So I wrote here, just to remind myself what I'm doing, I wrote to show, and then I wrote P and Q, and then there's this funny looking new symbol that I'll take just a moment to explain, and then after that, Q and P. This new symbol is called, actually, it's usually called the sequent symbol. That's just a funny old name that some logicians invented. So the sequent symbol. In terms of typography, it's often called the turnstile. Now, in truth, what this is supposed to indicate, the turnstile, is that there is a valid argument that begins with the thing or things to the left of the turnstile and ends with the thing on the right. So what I'm showing is there is a valid argument that starts with P and Q and that ends with Q and P. So what is a valid argument? Well, it's exactly the thing we were just looking at. It's some lines, numbered lines. Each line is justified by one of the rules you're permitted to use. Okay, so now, in one sense, I face this situation of terrible freedom because no one's going to tell me what to do next. I've been asked to show something, but I can show it any way I want as long as I follow the rules. This case, it's pretty obvious what a good idea would be to do in this case, because the premise that I need to begin with is P and Q. So I'll write that down, P and Q, and that's my assumption. That's justified by the rule of assumptions. That's my first line. Now, this proof won't require a lot of strategy and forward thinking. It's fairly easy to just crank through this one. But in general, it's good when you're writing a proof to think forward and backwards. That is, think what you can take away from your premises and think what you need to get to your conclusion. Our conclusion here is Q and P. We know we could get that from and introduction if we had Q on a line and P on a line. Now, this is totally obvious, right? But of course, we can get those from the conjunction P and Q. So let's just, that thought process, write it out. So what I do is I write down P, that's one and elimination. I write down Q, that's also one and elimination. Remembering, and elimination lets you peel from either the left or the right side, from the left conjunct or the right conjunct. And then finally, I write Q and P. And introduction, like and elimination, lets you do it either way. And so now I can put the Q on the left and the P on the right. Now, I'll just be a little bit careful here in citing. When I give my justification, I'm actually going to write the numbers in the order I use them. So I'm going to actually write here 3, 2 and introduction. That is because 3 was the line that came first. That is Q on line 3 got used first in the conjunction. Okay. So now I'm finished because every line here was permitted by the rules. The first line was the thing to the left of the turnstile. The last line is the thing to the right of the turnstile. So it's a valid proof. Pretty simple. Now, you might ask yourself, why not just say as a rule, Q and P follows from P and Q? Why not just say, for those of you who are slightly more mathematically oriented, why not just say that and is commutative? That is, and can be reversed. Now, this is actually a deeper question you might think, because in fact, we have really two extreme options in presenting logic. One is to give you lots of rules and make you memorize a lot. And if that was the strategy, I would give you commutativity of and, that is, you can flip and as a basic rule. My strategy is to give you fewer rules, less to memorize, and then ask more of you in proving stuff. So I'm going to ask you to use those rules to prove a lot of stuff. The method behind that madness is I want you to think. I won't want you to memorize. I want you to reason. And so I'm going to give you fewer rules so you do more reasoning, less memorization. Okay, so we've seen a valid proof. If I can successfully turn my page, we'll do another one. Okay. So here, what I want to show is two things. Okay, the first thing is I'm going to show that this is one of the most boring valid arguments you'll ever see. You might even consider it sort of the repeating yourself argument. It says, from P, one can derive P and P. Okay, so it's not normally the kind of thing you'd think I'm going to prove that. So the reason we go through this exercise is to see what our rules can do, right? Remember, the thing about logic is logic almost wants you to pretend that you're not very smart. It doesn't want you to use your brilliant intuition. The problem with brilliant intuition is not everybody sees it. Logic wants you to make things so explicit that anybody can see why it's right. So we don't want you to jump from the assumption P to P and P, even though that's obvious. We want you to tell us what rules permitted you to do that. So we can all agree that we agree on the basic rules and we agree that the rules were applied correctly, so that follows. Okay, so in this case, it's going to be pretty easy, right? So we start with P, that's an assumption, that's the thing to the left of the turnstile. Now, how do we get P and P? Because don't we need two lines? Now, the funny thing is, two in logic sometimes just means, it doesn't mean two different, it just means two. So it's as if I told you, I have two apples, where in fact what I have is one apple, I pull it out of a bag, I put it back in the bag, and I pull it out again. Well, that is permitted with premises in logic, is you can use the same premise twice. So actually, I can apply and introduction to line 1 2 times over, and that gives me P and P on line 2. So it's a nice short proof, 2-line proof from P to P and P. Now, on the top there, I wanted to show not just that P and P follows from P, but P follows from P and P. Actually, the second one is easier than the first. It doesn't even require any reasoning about how the rules work. You just go from P and P, your assumption on line 1, and then you apply and elimination one time, and you get P. The reason I include that second half is because actually this is now an example of two things that are logically equivalent. They're provably equivalent. P on the one hand, P and P, they're different, right? One is repetitive, P and P. P is not repetitive, but they mean the same thing. They're true in the same conditions. You can prove the one from the other, so they're actually equivalent to each other. Okay, so that gives us an example of using both introduction and elimination of and. Notice, by the way, we've got now that and is commutative. You can't assume it's commutative. That is P and Q. You can get Q and P. You can get it by an argument. We also have and is what you might call idempotent. That is, you can reproduce things. P is the same as P and P is the same as P and P and P, etc. So one more example in this session, and that is and is, not surprisingly, but this is something we can prove, and is associative. That is where you put the parentheses. So remember, I'll write this up here, just look, one of the problems with learning logic for clever students is logic seems to slow you down sometimes because you already know, for example, that and is associative. You don't think, if I say P and Q and R, I need to choose where to put my parentheses in because it doesn't matter. Okay, but logic is for simpletons, right? Logic is the reason we have computer science, because the thing is, computers need to have everything made very explicit. Okay, so remember this, if I just wrote something like this, P and Q and R, if I tried to write that, and if I ran that through a syntax checker, a logic syntax checker, it would say, no, that's ill-formed, because when you put two things together like P and Q, then you'd have to put the parentheses around, and then R would come after that parentheses. Or you could do it the other way around. You could put Q and R together, put on parentheses, and then put Q on. So you have to choose one of the two. There's no two ways about that. But now we'll prove here, this thing on the right, we'll prove that the one can be derived from the other. Okay, so now this argument is not challenging, it's just a little bit tedious. The truth is actually many things in logic. Another way you might put one of the great insights of logic is things that seem brilliant and very, very difficult actually turn out to be kind of trivial, just tedious, and take lots of little steps. Okay, so in this case, to get this parenthesis shifted to the right, we start here again with our assumption of P and Q in parentheses and R. And then we want to get at the end P and Q and R. Now looking at the second thing, so remember I said reasoning from the premises and thinking what you can get from them, and then looking at your conclusion, keeping your conclusion in mind. It's your destination where you want to get, and asking yourself, how can I get there? What do I need to get there? In this case, well, you need P, you need Q, and you need R, but basically what you need is you need Q and R first. They don't necessarily have to come first, but you need them, and you need to put those together first, and then put them together with P using conjunction introduction. So the strategy is clear. If you look at the premise here with P and Q in parentheses and then R, just pull it all apart. Get P and Q and R all on separate lines. So we'll just start by pulling R out. So from 1 and elimination. Then we get P and Q out. Again, 1 and elimination. And now on line 4, we can peel out P, 3 and elimination, and Q, 3 and elimination. And now we've pulled everything out of our first long conjunction, put it back together again in the right order that we need. So now we put Q and R together, so that goes from 5 and 2. So 5 and 2 and introduction. And then finally, take our P from line 4. So 4, 6, and introduction. And that's our conclusion that we wanted. Okay, so there we've proven that and is associative, just from the assumption that ands can be eliminated. So given a conjunction, you can peel off either conjunct, and can be introduced. If you have things on two lines, any two lines, you can put those together on a single line with a conjunction symbol between those, conjunction introduction. The only tricky things here are, remember that you have to apply these rules to entire lines. So in other words, if you have, I'll just give you an example of a no-no, just so you're sure you understand how this works, right? So even if you have something that looks like, if you have something like this, P or Q and R, you might be tempted, the temptation might arise to write on the next line something like this and write and elimination. Okay, but that, what I've just written, is a no-no. This is wrong, because the form of the and elimination rule is what's on the line from which you eliminate and must be a conjunction. It must be two things, like I said at the start, phi, psi, put together by a conjunction. There can't be anything else. So in this line here that I wrongly applied and elimination to, it's a disjunction. It's P or, and then the conjunction is in parentheses. I can't touch that conjunction, that Q and R, because it's not on the line by itself. So and elimination doesn't apply to that line. Okay, so don't apply and elimination unless the line itself is a conjunction. And introduction is easier, or it's easier to not make any mistakes. It's harder to make a mistake because you just take things from two lines and you put them together with a conjunction symbol between. Good. So this session will stop here. It's not easy to prove much with just and elimination and introduction. In order to start proving some more exciting things, we'll need a few more rules. In the next segment, we'll introduce or introduction, conditional elimination, which is modus ponens, and a couple rules for double negation.